Because we used logarithms to solve exponential equations, you might anticipate the need for exponential functions in solving logarithmic equations, and you would be right. But before we jump into logarithmic equations, we need to be aware of a few logarithmic properties first. So we'll examine some basic properties and the expanding and condensing properties of logarithms. Let's start with the basic properties. So if we have to evaluate log base a of 1, that is log with any base and the argument is 1. Now think about this. A logarithm represents an exponent. So I'm trying to figure out what exponent can I raise a to in order to get 1. Well, anything raised to the 0th power is equal to 1. So because the exponent is 0, we can evaluate that logarithm as 0. So anytime you see a 1 in the argument position of a logarithm, no matter what the base is, it will always evaluate to be 0. Let's look at the next one. We have log base a of a. Again, we're trying to figure out base a to what power equals argument a. Clearly, the only exponent that works there is 1. So if you see a logarithm where the base and the argument match, then the exponent that connects the two is always going to be 1. Now on the next one, we have log base a of a to the x power. Again, we're trying to figure out a, base a raised to what power equals the argument a to the x. Clearly, the exponent there is x. So if this base matches this base, then the answer is just the exponent. The logarithm represents the exponent, so it's like I'm just gleaning the exponent off of that argument there. And then finally, we have a raised to the log base a of x. This is also equal to x, although it might not be as clear why. To begin with, notice that exponent is logarithmic. That is, that log base a of x represents the exponent that I can raise a to in order to get x. And notice I'm raising a to that exponent. Therefore, I get x. Now, if you didn't follow that explanation, check out this note. Properties 3 and 4 are the result of composing exponential and logarithmic functions. Now, we've learned that if f and g are inverse functions, then we can compose them in either order and get x. That is, f composed with g of x is equal to g composed with f of x, which is equal to x. So let's assume that f of x represents the exponential function a to the x, and g of x represents the logarithmic function log base a of x. Now we know these are inverse functions. So when I compose inverse functions, I always get x. So it must be true that x equals f composed with g of x. So let's see what this expansion looks like. That is f of g of x. So I'm going to replace that inside function g of x with its rule log base a of x. And then we're going to plug that argument into the function f. So I'm going to take what's inside parentheses there and plug it in for that argument. So we have a to the log base a of x. And notice that establishes property number 4. Similarly, we can compose them in the other order and still get x. That is, x equals g composed with f of x. Or x is g of f of x. This time we begin by replacing the inside function f, which is a to the x, and then we're going to take that argument a to the x and plug it into the function g where I see the argument. We obtain log base a of a to the x. So this one verifies property number 3. So you can certainly prove it with composition, but you want to be familiar with these basic properties in order to quickly evaluate and simplify these logarithmic expressions. Let's try this on example 1. Use the basic properties of logarithms to evaluate the following logarithms exactly. So on example A, we have log base 5 of 5. Notice the base of the logarithm and the argument match. This follows the pattern of property number 2. So we end up with 1. Log base 5 of 5 is equal to 1. The next one, we have natural log of the cube root of e. Since we're dealing with a natural log, even though it's not written, we understand that base to be e. We can think of natural log of the cube root of e as natural log of e to the 1/3. So in this case, the base of the logarithm, again, it's not written, but we know that it's e, matches the base of the argument. So this is going to follow property number 3. If the base of the logarithm and the base of the argument match, then the result is the exponent, which is 1/3. Next, we have natural log of 1. Again, we're dealing with a base e logarithm, but notice the argument is 1. This follows the pattern of property number 1. Log of any base of 1 is always equal to 0. And then finally, we have 3 to the log base 3 of 2. This follows the pattern of property number 4. So the answer there is just the argument. Each one of those problems you could certainly type into your calculator to verify the value. But being familiar with those properties, again, will be beneficial when we need to quickly simplify terms in an equation. Beyond those basic properties, we also have expanding and condensing properties, which are a little bit more challenging. We're going to look at 3 varieties of expanding and condensing properties: the product property, the quotient property, and the power property. Now, all of the arguments of our logarithms are going to be assumed to be positive, and we're going to be dealing with a base a that's positive and not equal to 1. So let's take a look at that first one, the product property. We have log base a of xy. Notice inside the argument of the logarithm, we are multiplying 2 factors together. That's x times y, or the product of x times y. This is going to be equivalent to log base a of the first factor x plus log base a of the second factor y. So each of those 2 original factors gets its own logarithm. And notice if we're multiplying in the argument position, we're going to convert that into addition between the 2 logarithms. Now this seems kind of foreign and unfamiliar, but you know the equivalent of this property in exponential form. So let me remind you of that. Recall that if we are multiplying like bases, that is, we're multiplying a to the nth times a to the nth power, then we can simplify this by adding the exponents. That is, we take multiplication in this position and convert it into addition in this position. Just like we take multiplication between the factors of the argument and convert it into addition between the logarithms. This also occurs with our quotient property. We have log base a of x divided by y. And we're going to convert this into log base a of the numerator x minus log base a of the denominator y. So division between the arguments of a logarithm converts into subtraction between the individual logarithms. You know a similar property with exponents, that is, when we're dividing like bases, we subtract the exponents. So division in one location converts into subtraction in another location. And then finally, we have the power property. If we have log base a of x raised to the p power, we can actually take that exponent on the argument and move it down as a coefficient. So the parallel to this one in exponential form would be the situation where we have a power raised to another power. When we have successive powers, we learned to multiply the powers, right? A power raised to a power, we multiply the powers. Now, we can see that p was the power or exponent on the argument, and we also have to remember that a logarithm represents an exponent or a power. So ultimately here, we do have the product of 2 powers. So let's see how we can apply these properties. If we read these properties from left to right, we call them expanding properties. But if we read them from right to left, we call them condensing properties. So let's look at the expansion direction. On example 2, we want to expand each expression. Write each as a sum or a difference of logarithms, and we don't want to include any exponents in the final arguments. And we're going to assume all variables represent positive real numbers, so our logarithms are defined. So on example 1, we have log base 2 of xy squared divided by z cubed. The first thing I notice about this argument is that we're dealing with a quotient. So we're going to apply the quotient property. That is log base 2 of the numerator, xy squared, minus log base 2 of the denominator, z cubed. So we have log of the numerator minus log of the denominator. But notice our first logarithm contains a product in the argument. So next we can apply the product rule and expand that logarithm a little bit further. So each factor in the argument is going to get its own logarithm, and then we're going to add those logarithms together. So we're going to have log base 2 of the first factor x plus log base 2 of the second factor y squared, and we still have this log base 2 of z cubed out here. Now notice our arguments still have exponents, so we're ready to apply the power property. That is, we're going to take a power on the argument and move it down in front as a coefficient. So we'll take this exponent 2 and move it down as a coefficient. This exponent 3 will also move as a coefficient. So our final expanded logarithm is going to look like log base 2 of x plus 2 log base 2 of y minus 3 log base 2 of z. Our resulting arguments don't have any operations applied. They're not multiplied, divided, and there's no powers. So we say that it's completely expanded. Let's try this on the next example. We have log base 5 of 25 times x squared minus 16. Now notice here we have a polynomial that could be factored. Let's begin by breaking that down into two factors. So we have log base 5 of 25 times x plus 4 times x minus 4, just factoring the difference of two squares there. Then we have three factors, 25, x plus 4, and x minus 4. So each individual factor is going to get its own logarithm. So this will expand as log base 5 of the first factor, 25, plus log base 5 of the second factor, x plus 4, plus log base 5 of the third factor, x minus 4. Now the first term, log base 5 of 25, can be evaluated. Remember, a logarithm represents an exponent. So I'm trying to figure out what exponent can I raise the base 5 to in order to get 25. Well, 5 squared is equal to 25, so the exponent represented there is 2. Now, it also may be tempting to want to distribute your logarithm into the argument on the next two terms. That feels like a natural thing to do, but it doesn't work with logarithms. You cannot distribute a logarithm across a sum or a difference. Notice if you have a product in the argument, you can separate it into a sum, but not if you have something added or subtracted in the argument. So we're just going to leave this log base 5 of x plus 4 plus log base 5 of x minus 4. And that logarithm then has been completely expanded. Okay, let's go the other way. On example 3, we want to condense each expression as a single logarithm with a coefficient of 1. Again, assume all variables represent positive real numbers so that our logarithms are defined. So in this one, we're going to start with the power rule. That's where we finished on the previous examples. But we want to take any kind of a coefficient and move it up into the exponent position. So I'm going to rewrite this, log of a. Now I'm going to leave the minus here and move the 2 into the exponent position. So we have b squared plus log of c raised to the 1/2 power. And do observe, this logarithm is missing a base, so we would assume that it has the common base, base 10. Okay, we're going to condense this into a single log base 10, and we're going to have a single argument. Now, we're going to do this all at once. So remember, if the argument comes from a positive logarithm, that argument is going to end up in the numerator. But if the argument comes from a negative logarithm, it's going to end up in the denominator. So on that one, we could just apply our quotient rule. A is in the top, b squared is in the bottom. But I'm going to go ahead and extend it over here and see, well, c to the 1/2 comes from a positive logarithm, so that factor is also going to end up in the numerator. So we could have a times c to the 1/2. And if you prefer, remember that c to the 1/2 could also be written as square root of c over b squared. So our logarithm has been completely condensed. For our last example, we're going to again start in the same place and move those coefficients to the exponent position. So I'm going to start by rewriting that first term as natural log of x to the 1/2. And I don't see any necessary changes for the other two logarithms. Now we want to condense this into a single logarithm with one argument. If the argument comes from a positive logarithm, it's ultimately going to land in a numerator. So we'll have x to the 1/2 and 2y in the numerator. But if the argument comes from a negative logarithm, that argument will land in the denominator for our condensed logarithm. So in the top, we're going to have x to the 1/2 times 2y, and in the bottom, we'll have x squared y. Now, our logarithm is completely condensed, but our argument does need to be simplified. Notice we can cancel the y's. And then we're dividing like bases, x to the 1/2 divided by x squared. So if I subtract those two exponents, the difference between 2 and 1/2 is 1.5 or 3/2. But because I have more x's in the bottom than in the top, the leftovers will end up in the bottom. So we'll have x to the 3/2 in the bottom. Don't forget that 2 left over in the top. So that logarithm has been completely condensed. So evaluating logarithms, expanding logarithms, and condensing logarithms, those will be necessary skills within the context of solving logarithmic equations. And we'll check this out in the next video.